Hello everyone, my name is Kawthar Saegh and I'm going to explain to you our Six Sigma project on the improvement of a PVC pipe production. The outline of our project is as shown: introduction, literature review, methodology, conclusion, and references. To start with, as we all know, Six Sigma uses a set of tools and techniques to improve a process or to decrease the defect rates or the cycle time or the waste products within a process. So as a group, we decided to apply Six Sigma on one of the major industries in Kuwait called National Industries Company, which produces many different types of construction products, but we chose to focus on the PVC industry, to be specific on two products, pipes and fittings, as shown, and their pictures are shown on this slide. As for the literature review, we found 25 different articles on the application of Six Sigma, and we divided them into 5 different categories according to their industries, and these articles helped us with the flow of our project. For the methodology, we decided to use the MAKE methodology, and this consists of 5 steps, which are define, measure, analyze, improve, and control. In the define phase, we created a SIPOC table to show the flow of the process from the beginning until the end. We also created a project charter table to define our problem statement as the following. National Industries Company is having an average of 2% defective pipes per month, and this costs them a loss of 568 kd. And for the goal statement, our objective or our aim is to improve the defect rate of the pipes by 10% and decrease NIC's financial losses. As for the project scope, which is the boundaries of our study, it will circulate around the pipes and the fittings production process. The project plan was also created to help us organize our time and finish our project on time, and the team members are as shown on the slide. Moving on to the measure phase, we calculated the average defect percentages for each month for the year 2018, and by comparing them together, we can see that January has the highest defect rate of 0.89%. So we chose to focus on the month of January 2018 for the calculations. Now, to benefit the company the most, we have to choose between fittings and pipes. And to do this, we created 2 bar graphs for January 2018 to look at the average defect percentages in each extrusion line, which produces pipes, and in each molding line, which produces fittings. And by comparing them, we can see that extrusion line 3 has the highest defect rate of 2%. And from the molding line bar graph, molding line 6 has the highest defect rate of 2.22%. Now, to make a decision, we also related these defect rates to cost. As shown here, we calculated the cost of defective pipes in extrusion line 3 and the cost of defective fittings in molding line 6, and we found that the cost of the pipes are around 568 kd, which is equivalent to 7,000 United Arab dirhams, and the cost of fittings are 17 kd, which is equivalent to 200 dirhams. So comparing them, we chose to focus on pipe production and to be specific on the 200 millimeter pipe, which has the highest cost and highest rejected quantity between the other pipes. Now, to understand the cause of the defects, we collected daily rejection sheets from the company, and we found that most of the defective pipes were due to problems with wall thickness. Wall thickness is measured at 8 different points as shown in the figure on the right, and if any one of the points from A to H is below or above the specification limit, then it is considered to be defective and is recycled. Therefore, we collected raw data from the company and inserted into Minitab as shown in the slide to be able to find the process capability report for the average wall thickness of the current process. From this process capability report, we can see that we have bars out of the specification limits, and our process capability of 1.09 is not equal to our process capability index 0.91, which indicates that the process is not centered and has to be improved. We can also see that the defective parts per million is around 9,657, and this is really high. And from the sigma conversion chart, we understand that the sigma level they are currently operating at is 3.7 sigma level, which can be improved. Now, in the analyze phase, we had to look at the process in details, and we found all the factors that affect the process. These are torque, screw speed, feeder speed, temperature, and vacuum pressure. And we understood that every 2 hours, a quality inspector would choose a pipe at random, takes it to the laboratory in the company, and uses vernier calipers to check the wall thickness of the pipe at 8 different points, as indicated in the photo on the right. And if any one of these points from A to H is above or below the specification limit, then the pipe is recycled, is considered defective, and is recycled. We drew an Ishikawa diagram to understand the different effects or different causes on our wall thickness defect. And after looking deep into the production process and talking to the company, we understood that torque and feeder speed are the 2 factors that are highly related to wall thickness and might cause these defects. Therefore, to understand whether these 2 factors and their interaction significantly affects the points on the wall thickness, we decided to use response surface methodology to check this, and we used the previous data that was seen on slide 13 from Minitab to do this. The results we found were that points C, G, and H from the wall thickness of the pipe are significantly affected by torque and feeder speed, and they're the ones with the highest defect rate, causing the pipes to be defective. We also decided to use XBar charts to check whether the process is currently out of control or in control for the 3 significant points. And these are the equations we used with the help of Minitab to draw the charts. These 2 charts are for points C and G, and from here we can see that there is outliers above and below the control limits, which shows us that the process is out of control and needs improvements. This is also the XBar chart for the 3rd significant point H, and we can also see outliers here. So the process is out of control, and we have to find a solution for this. Contour plots are used to decide on the optimal levels of several factors acting on a specific response. In our case, the legend, which is color-coded, represents our response wall thickness, and we use this color-coded legend to search for the correct optimal level of both torque and feeder speed, where it will provide us with wall thickness between the customer specification limits in order to avoid defective pipes. And after applying this to our 3 responses, C, G, and H, we were able to find the optimal levels. Now, from these 3 graphs, we understood that the feeder speed optimal level should be reduced to between 28 to 29.5 rounds per meter. And the torque level the company is using is very broad and should be narrowed between 60 to 62.5% in order to avoid defective pipes. The next step we did was looking at all the out of control signal data points that we found on the XBar charts shown on the previous slides, and we checked the data for each out of control signal point in Minitab to see whether the torque range was out of the optimal settings that we provided if this was correct, then that data point would be removed from the Minitab data. For example, for point C, the data point 2 was out of control, and when we come here to look at data point 2, we can see that the torque is 59.9%, which is below 60%, and this explains why it produced a defective pipe. So we removed this data point. The same procedure was followed for all out of control signal data points. After removing all the out of control data points, we redrew the XBar charts for these 3 significant points, and from here we can see that all data points are now between the control limits and the process is in control. The 1 or 2 outliers that you see are due to chance. This is the third XBar chart for the third significant point H, and is also showing an in-process control. And this proves to us that our solution is beneficial and solved the problem. We also redrew the process capability report after improvements were made. And we can see that now all the bar graphs, all the data points are between our specification limits, and our process capability increased. And we can also see that our defective parts per million decreased to 989, which indicates to us 89% improvement, as well as the sigma level increased from 3.7 sigma level to 4.7 sigma level. The next step was producing an out-of-control action plan flowchart for the workers or the employees, so that when an out-of-control signal is seen on an XBar chart or an XBar chart, they'd follow this flowchart in details and they'll understand the correct action to take. This is the continuation of the flowchart for the correct actions to take by the employees. To conclude, we found that pipes were defective due to wall thickness, and we used response surface methodology to determine whether the factors we found significantly affects our defect, and we used contour plots to provide us optimal settings for feeder speed and torque. And after improvements, we found that the process is in control and defective parts per million decreased significantly. And these are the references that we used. Thank you very much.